Now, in this lecture, we will find out the length of line segment AE. In the drawing, we have rectangle ABCD. We know that side AD equals to 3 units in its length. Inside this rectangle, we have those two semicircles. The radius of this big semicircle is 2. The radius of this small semicircle is 1. And our mission is to find out the length of this line segment AE. So first of all, we know that all the angles inside any rectangle are right angles. So those 4 angles, they are all right angles. So okay, this is a right angle. This is also a right angle. This is a right angle. And this is angle ABC, that is also a right angle. So, in the next step, we will define the relevant points for this question with letters. We will define the center of this big semicircle. This point is point P. Likewise, we will define the center of this small semicircle. This point is point Q. We'll define the touching point of those two semicircles. This point is point S. We'll define the point of tendency of tangent AE with this big semicircle. This point is point L. And finally, we'll define the point of tendency of tangent AE with this small circle. This point is point G. In the next step, we will do a construction. That is to say, we will extend line segment AE and this side DC by a straight line until they touch each other. So this is their touching point. We define this touching point as point F. Okay, so here we have side DC of rectangle ABCD. It is definitely a straight line. Then we extended the straight line DC by a straight line, and the result is DF. When you extend the straight line by a straight line, the result must be a straight line. Therefore, DF is a straight line. If we focus on the upper side of the straight line, DF at point C, here the sum of the angles must be equal to 180 degrees, according to the rule that the sum of the angles, all three, that says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of DF at point C? We have here this angle that is a right angle plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So here we have the small right triangle ECF. We will define this angle EFC as alpha. So in the small right triangle ECF, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, we focus on the big right triangle, triangle ADF. In the big right triangle, triangle ADF, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this third BC angle must be equal to 90 degrees minus alpha, according to the sum rule that says that the sum of the angles in any triangle is equal to 180 degrees. So here we have DP, 97 DP is the radius of this big semicircle, that is 2, and PS is also the radius of this semicircle, that is 2. So I write it down. QS is the radius of this small semicircle, that is equals to 1. QC is also the radius of this semicircle, that is equals to 1. And finally, CF, line segment CF, is unknown. So we define the length of this line segment CF as X. So we have here the radius PL of this big semicircle is drawn to point L, that is the point of tendency of tangent AE with this big semicircle. So here we can implement rule 1. So I repeat quickly rule 1. According to rule 1, a tangent to the circle is perpendicular to the radius drawn to its point of tendency. So in the drawing we have a circle, and we also have here tangent AEB, that is tangent to this circle at point M. Point M is the point of tendency of tangent AEB with this circle. In addition, we have the radius OM, that is equals to R. The radius OM is drawn to point M, that is the point of tendency of tangent AEB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AEB will be perpendicular to the radius MO. If AEB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to this rule, rule 1. So we can actually implement rule 1 in our drawing. Why? Because in our drawing, we have the radius PL is drawn to point L, that is the point of tendency of tangent AE with this big semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent PL will be perpendicular to the tangent PL will be perpendicular, the radius PL will be perpendicular to tangent AE, or tangent AE will be perpendicular to the radius LP. Again, tangent AE will be perpendicular to the radius LP. If AE is perpendicular to LP, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we have the radius QG of this small semicircle. The radius QG that is equal to 1 is drawn to point G, that is the point of tendency of tangent AE with this small semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent AE will be perpendicular to the radius GQ. If AE is perpendicular to GQ, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to the sum rule, rule 1. So in the next step, we will prove that the big right triangle, triangle LPF, is similar to this small right triangle GQF. So right now, we will prove that the big right triangle, triangle LPF, is similar to the small right triangle, triangle GQF. Why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. So actually this is angle PLF, in the right big triangle, LPF, and it is equal to this angle, this is actually angle QGF. In this one right triangle, GFQ. So repeat again. If we found out that angle PLF in the big right triangle LPF equals to angle GQ to angle F to angle QGF in the small right triangle GQF, they are both equal to 90 degrees and therefore they are equal to each other. In addition, this is angle alpha, that is a common angle that belongs to both triangles. So if I know that angle alpha equals to itself, it's a common angle that belongs to both triangles. So if we relate to this angle alpha as it is belongs to the big right triangle LPF, it will be defined as angle LFP. And angle alpha equals to itself. So if we relate to angle alpha as it belongs to the small right triangle GQF, it will be defined as angle GFQ. Repeat again. This equation means that angle alpha equals to itself. We just go to angle alpha two different names. Angle alpha equals to itself is a common angle that belongs to both triangles. And finally, those here we have in the right big triangle LPF, this angle equals to alpha, this angle equals to 90 degrees, this angle equals to alpha, therefore this first angle must be equal to 90 degrees minus alpha. Likewise, in the small right triangle GQF, this angle equals to alpha, this angle equals to 90 degrees, therefore this first angle must be equal to 90 degrees minus alpha, according to the same rule that says that the sum of the angles in any triangle is equal to 180 degrees. So those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So this is angle LPF. The big right triangle LPF, and it is equal to this angle, that is actually angle GQF. In the small right triangle GFQ. Okay, again, we should found out that angle LPF in the big right triangle, LPF equals to angle GQF in the small right triangle, GFQ, they are equal to 90 degrees from alpha, therefore they are equal to each other. So we should find out that all the triangles in this big right triangle LPF are correspondingly equal to all the triangles inside this small right triangle GQF, and therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down. So the big right triangle LPF is similar. This is the sign of similar to the small right triangle GQF according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side LP in the big triangle or side GQ in the small triangle equals to side PF in the big triangle or side QF in the small triangle. So again, we derive that LP over GQ equals to PF over QF. LP is 2, it is the radius of the big semicircle, that is equals to 2 units, over GQ. GQ is 1, it is the radius of the small semicircle, and it is equals to PF. PF in total equals to 2 plus 1 is 4 plus x. Again, in total, PF equals to 2 plus 1 that is 4 plus x. So PF in total equals to 4 plus x. Over QF. QF in total equals to 1 plus x. So we found out that 2 equals to 4 plus x over 1 plus x. Here we multiply this equation by 1 plus x. And we get that 2 times 1 plus x equals to 4 plus x. So here we'll open the brackets on this side of this equation, and we get that 2 times 1 is 2 plus 2x equals to 4 plus x. Here we subtract x from this equation, and we get that in this side of the equation we have 2x minus x is x. So in total, in this side of the equation we have 2 plus x, that equals to x minus x is 0. So in this side of the equation we have 4. So 2 plus x equals to 4. We subtract 2 from this equation, and we get that x equals to 4 minus 2, that is 2. So we should find out that the length of line segment CF is equals to x is equals to 2 units. So I write it down. In the next step, we will prove that the big right triangle ADF is similar to the small right triangle ECF. So write it down. We will prove that the big right triangle ADF is similar to the small right triangle, this small right triangle is here. Triangle is here. So why the big right triangle ADF is similar to the small right triangle is here. First of all, those two angles are both equal to 90 degrees and therefore they are equal to each other. So actually this is angle ADF. In the big right triangle ADF, and it is equal to this angle, it's actually angle ECF. In the small right triangle EFC. So repeat again. I will found out that angle ADF with the big right triangle ADF equals to angle ECF with the small right triangle EFC. They are both equal to 90 degrees and therefore they are equal to each other. In addition, this is angle alpha, that is a common angle that belongs to both triangles. So you can write down that angle alpha equals to itself is a common angle that belongs to both triangles. So if we relate to this angle alpha, since it belongs to the big right triangle AFD, it will be defined as angle AFD. And the angle alpha equals to itself. So if we relate to this angle alpha, since it belongs to the small right triangle ECF, it will be defined as angle EFC. So this equation means that angle alpha equals to itself. We just call to angle alpha two different names. Angle alpha equals to itself. It's a common angle that belongs to both triangles. And finally, those two angles, they are both equal to 90 degrees on circle, therefore they are equal to each other. So actually, this is angle DAF. In the big right triangle AFD, and it is equal to this angle, that is actually angle CEF. In the small right triangle EFC. So repeat again. Actually, found out that angle DAF, the big right triangle AFD equals to angle CEF. In the small right triangle ECF, they are both equal to 90 degrees on circle, therefore they are equal to each other. So we actually found out that all the triangles inside the big right triangle ADF are correspondingly equal to all the triangles inside the small right triangle ECF. And therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down. We actually found out that the big right triangle ADF is similar, this is the sign of similar to the small right triangle ECF according to angle similarity rule. from the fact that this big right triangle ADF is similar to this small right triangle ECF, we will derive that the following relationship exists between their sides. We will derive that side AD, the big right triangle ADF, over side EC, the small right triangle ECF, equals to side DF in the big right triangle ADF over side CF in the small right triangle ECF. So again, we will derive that side AD, the big triangle, over side EC in the small triangle equals to side DF in the big triangle over side CF in the small triangle. AD equals to 3 units in itself, according to what is given as the question, over EC. EC is the missing side, so we leave it as it is. And it is equals to DF. DF in total equals to 2 plus 2 plus 2, that is 6, plus 1 plus 1, that is in total 8. Again, DF in total equals to 8. Over CF. CF equals to 2. So in conclusion, we have found out that 3 over EC equals to 8 over 2. 8 over 2 is 4, so I write it down. So we have found out that 3 over EC equals to 4. Here we will multiply this equation by EC. And finally we get that 3 equals to 4 times EC. Here we'll divide this equation by 4. And finally we get that the missing side EC is equals to either 3/4 or 0.75. So write it down. If you found out that the missing side or line segment EC equals to either 3/4 or 0.75 units. What is the length of side BC of rectangle ABCD? Again, what is the length of side BC of this rectangle ABCD? We know that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side AD must be equal to the opposite side BC. But AD equals to 3, therefore BC must be also equal to 3 units in its length. So if we found out that BC equals to 3, what is the length of the missing line segment BE? From the normal, it is very easy to see that BE in total equals to BC minus CE. Again, BE equals to BC minus CE. So BE equals to BC, BC is 3, minus CE. CE is 0.75. So in total, I shall find out that BE equals to 3 minus 0.75, that is 2.25. So this missing line segment BE is equals to 2.25 units in its length. Here we use the same rule that says that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side AB must be equal to the opposite side DC. Again, side AB must be equal to the opposite side DC in rectangle ABCD. But what is the length of DC? DC in total equals to 2 plus 2, that is 4, plus 1 plus 1, in total is 6. So in total DC equals to 6. And therefore the opposite side AB must be also equal to 6 units in its length. So in the next step, I'll copy the right green triangle ABE in a new page. And we'll implement the Pythagoras theorem in this green right triangle, triangle ABE. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the slopes of the perpendiculars. Here by PT is abbreviation for Pythagoras theorem. Side AB equals to 6 units in its length, and side BE equals to 2.25 units in its length. So actually, this is the right green triangle, triangle ABE, that are going from the original drawing. According to the Pythagoras theorem, in this right triangle, triangle ABE, AE squared, that is the square of the hypotenuse, must be equal to AB plus B. AE squared, that is the square of the hypotenuse, must be equal to AB squared plus BE squared. So write it down. AE squared, that is the square of the hypotenuse, must be equal to AB squared plus BE squared. AE is the missing side, so we will leave it as it is. And we get that AE squared equals to AB squared. AB is 6, therefore AB squared is 6 squared, that is 36, plus BE squared. BE is 2.25, therefore BE squared is 2.25 squared. That's actually equals to 5.0625. So in total, AE squared equals to 36 plus 5.0625. 36 plus 5.0625 equals to 41.0625. So if you found out that AE squared equals to 41.0625, here we take a root out of this equation, and finally we get that the missing line segment AE, that is the line segment that we are looking for in this question, is equals to the square root of 41.0625, and the square root of 41.0625 is equals to 6.408 units. And that is the answer to the question. Repeat again, if we found out that the length of this line segment AE is equals to 6.408 units. So in the next step, I will summarize the lecture. In this lecture, we found out the length of this line segment AE. So, in the drawing, we have rectangle ABCD. We know that side AD of this rectangle ABCD is equal to 3 units in its length. In addition, we know that inside this rectangle ABCD, we have those two semicircles. The radius of this big semicircle is 2, the radius of this small semicircle is 1. Again, our mission is to find out the length of this line segment AE. So first of all, we know that all the angles inside any rectangle are right angles. So those 4 angles, they are all right angles. In the next step, we define the relevant points to this question with letters. We define the center of this big semicircle, this point is point P. We define the center of this small semicircle, this point is point Q. We define the touching point between those two semicircles, this point is point S. We define the point of tendency of tangent AE with this big semicircle, this point is point L. Finally, we define the point of tendency of tangent AE with this small semicircle, this point is point G. In the next step, we did the construction. That is to say, we extended line segment AE and side DC by straight line until they touch each other. This is their touching point. We defined their touching point. This point is point F. So here we know that DC is one side of rectangle ABCD, and therefore it is absolutely a straight line. Then we extended the straight line DC by straight line, and the result is DF. When we extend the straight line by straight line, the result must be a straight line. Therefore, must be a straight line. DF is a straight line. So if we focus on the upper side of the straight line DF at point C here the sum of the angles must be equal to 180 degrees, according to the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of DF at point C? We have this angle that is right angle plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we actually focused on this small right angle, triangle ECF. In this small right angle ECF, we define this angle EFC as alpha. So in the small right triangle ECF, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees round to alpha. Why? Because 90 degrees round to alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, we focus on the big right triangle ADF. In the big right triangle ADF, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees round to alpha, according to the same rule that says that the sum of the angles in any triangle is equal to 180 degrees. Okay. So here we have dP is the radius of this big semicircle that is 2. PS is also the radius of this big semicircle that is equal to 2. Likewise, QS is the radius of this small semicircle that is 1. QC is also the radius of this small semicircle that is 1. And finally, CF is the missing line segment, so we define the enough of this missing line segment CF as X. Here we have the radius PL that is equals to 2. The radius PL is drawn to point L, that is the point of tendency of tangent AE with this big semicircle. And whenever we have a radius that is drawn to the point of tendency, then tangent AE will be perpendicular to the radius LP. If AE is perpendicular to LP, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we have the radius QG of this small semicircle. The radius QG that is equals to 1 is drawn to point G, that is the point of tendency of tangent AE with this small semicircle. And whenever we have a radius that is drawn to the point of tendency, then tangent QG will be perpendicular to the radius AE. If QG is perpendicular to AE, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. So, in the big right triangle LPF, this angle equals to alpha, this angle equals to 90 degrees, therefore this third missing angle must be equal to 90 degrees minus alpha. Likewise, in the small right triangle GQF, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha according to the same rule that says that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we proved that the big right triangle LPF, this big right triangle LPF, is similar to this small right triangle GQF. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle alpha, that is a common angle that belongs to both triangles, so we can write down that angle alpha equals to itself as a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So if we prove that all the figures in the big right triangle NPF are correspondingly equal to all the figures in the small right triangle GQF, and therefore those two right triangles are similar to each other according to angle similarity rule. So again, we shall find out that the big right triangle NPF is similar. This is the sign of similar to the small right triangle GQF according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side LP, the big triangle, or side GQ, the small triangle, equals to side PF in the big triangle, or side QF in the small triangle. Repeat again. We will derive that LP over GQ equals to PF over QF. LP is 2, is the radius of the big semicircle, that is 2 over GQ. GQ is 1, is the radius of the small semicircle, that is 1. And this equals to PF. PF in total equals to 2 plus 1 plus 1, that is 4, plus x. Again, PF in total equals to 4 plus x over QF. QF in total equals to 1 plus x. So if we found out that 2 over 1 equals to 4 plus x over 1 plus x. Here we multiply this equation by 1 plus x, and finally found out that 2 times 1 plus x equals to 4 plus x. Here we open the brackets on this side of the equation and found out that 2 times 1 is 2 plus 2x equals to 4 plus x. Here we substitute x from this equation and finally found out that 2x minus x is x. So in total in this side of the equation we have 2 plus x equals to x minus x is 0. So inside this side of the equation we have to only with 4. So in total we actually found out that 2 plus x equals to 4. Here we subtract 2 from this equation and finally found out that x equals to 4 minus 2, that is 2. So if we found out that the length of this line segment CF is equals to x is equals to 2 units. In the next step, we proved that this big right triangle ADF is similar to this small right triangle ECF. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees and therefore they are equal to each other. In addition, this is angle alpha, that is a common angle that belongs to both triangles, so we can write down that angle alpha equals to itself is a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we proved that all the figures inside the big right triangle ADF are correspondingly equal to all the figures in the small right triangle ECF, and therefore those two right triangles are similar to each other according to angle similarity rule. So repeat again. And we found out that the big right triangle ADF is similar, this is the sign of similar, to the small right triangle ECF according to angle similarity rule. And from the fact that the big right triangle is similar to the small right triangle, we will derive that the following relationship exists between their sides. We will derive that side AD in the big right triangle ADF over side EC in the small right triangle ECF equals to side DF in the big right triangle ADF over side CF in the small right triangle ECF. Repeat again. We derive that side AD in the big triangle or side EC in the small triangle equals to side DF in the big triangle or side CF in the small triangle. AD is free, EC is the missing side, so we limit as it is, and it is equals to DF. DF in total equals to 2 plus 2 plus 2, that is 6, plus 1 plus 1, that is 2, so in total it is 6 plus 2, that is 8. So DF in total equals to 8 over CF equals to 2. So in conclusion, we found out that 3 over EC equals to 8 over 2. 8 over 2 is 4, so in total we found out that 3 over EC equals to 4. Here we multiply this equation by EC and finally found out that 3 equals to 4 times EC. Here we divided this equation by 4 and finally found out that the missing side EC equals to 3 quarters of 0.75. And again we found out that this missing side EC is equals to either 3/4 or 0.75. What is the length of side BC of rectangle ABCD? Again, what is the length of side BC of rectangle ABCD? We have the rule that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side AD must be equal to the opposite side BC. But AD is 3, therefore BC must be also equal to 3. Here BC is 3. What is the length of line segment BE? From the drawing, it is very easy to see that BE equals to BC minus EC. Again, BE equals to BC minus EC. So BE equals to BC, that is 3, minus CE, that is 0.75. So in total, BE equals to 3 minus 0.75. 3 minus 0.75 is 2.25. So in conclusion, we can find out that the length of side BE is 2.25. We use the rule, the same rule that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side AB must be equal to the opposite side DC. But DC equals to 2 plus 2, that is 4, plus 1 plus 1, that is 2, and 4 plus 2 is 6. So DC equals to 6, and therefore the opposite side AB must be also equal to 6. In the next step, I copied the right green triangle ABE in a new page, and we implemented the Pythagoras theorem on this green right triangle ABE. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So this is the right triangle the right green triangle ABE that is coming from the original drawing. Side AB equals to 6 units in itself, side BE equals to 2.25 units, and the length of the hypotenuse is unknown. So in this right triangle ABE, according to the Pythagoras theorem, the square of the hypotenuse is AE square, and it must be equal to AB square plus BE square. Again, AE square must be equal to AB square plus BE square. AE is the missing side, so we leave it as it is. So AE square equals to AB square. AB is 6, therefore AB square is 6 squared, that is 36. Plus BE square. BE is 2.25, therefore BE square is 2.25 square, that is 5.0625. So in conclusion, we should find out that AE square equals to 36 plus 5.0625. 36 plus 5.0625 is 41.0625. So in total, we should find out that AE square equals to 41.0625. Here we took a root out of this equation and finally found out that the missing 97 AE, that is the 97 that we are looking for in this question, is equals to the square root of 41.0625. The square root of 41.0625 is 6.48 units. So in conclusion, we can find out that the length of this line segment 97 AE is equals to 6.408 units. Okay, thank you very much.